And we are now recording. Okay, so while I'm setting up, I was going to do a similar strategy as yesterday. I'll lecture for a while, but I don't have to get that far. And then once I've done quote unquote enough, then I'll stop and maybe let you ask questions. And that'll be all of tomorrow also. Okay, so let's see if I can get us set up. Okay, so we're over here, 5.1. I'm still going to do 5.1. And after this, we only have 4 sections left and 3 weeks essentially. Okay, so again, tomorrow I'll dedicate the entire time to questions and answers. I'm not going to guarantee I'll do the whole thing because, as you know, and I know, some curve sketching problems take a long time. Okay, so I might refuse to do the entire problem. Likewise with some of the word problems. Some of the word problems are real long. So again, that's the reason why I gave you, a quiz which was quote unquote long, and a word problem that was quote unquote long. And I'm going to try to construct a test that you can finish it in an hour. We'll see how it goes. And yeah, the main thing about the test on Friday is do only what it asks. So I might say only do the first derivative test or only do the second derivative test. So if it doesn't ask for a graph, don't graph it. If it doesn't ask for concavity, don't give it. If it doesn't ask for max min, don't give it. Answer exactly what is there. Don't do any more, don't do any less, because if you end up trying to do more, then you waste time for being able to go on to the rest of the test. So I'm going to construct a test. So I say, okay, you may not have to do the entire thing, like some of the curve sketches, right? So give me the whole works, and there are 8 things, right? Domain, intercept, symmetry, asymptotes, increasing, decreasing, max min, concave up, concave down, inflection points, and then graph it. Okay, I may not have you do the entire thing because it just takes too long. Okay, so answer specifically what's there. So if your reason when you turn in a test and you complain, oh, I didn't have enough time to do the test, well, maybe you did more than was supposed to be, so you were wasting your time, right? So I say to myself, okay, I have a chance to test you on first derivative. I can test you on second derivative. I don't have to ask you that on every question, just certain parts of it. Okay, so just answer exactly what you see on the exam, no more, no less, and I'll try to construct a test so that it can be finished hopefully within the 1 hour that we have there. Okay. All right, so that's the game plan. So I'll lecture for quote unquote a while. And if I have time, I may stop and let you ask questions. So be ready. If you have any questions in preparation for the test on Friday, then think about what you want to do. So then we're sort of back on schedule. All that happened was I flopped the 23rd and the 30th there. So these got switched, but otherwise we would pretty much be on schedule after that. Okay. So any quick questions? Let me check the chat quickly. Okay, some people about attendance. All right. So anybody join late, always put your name in the attendance, and then I think we're good. Okay. So let's pick up where we were. And again, the exam will not cover anything I'm doing this week or even last week. So 4.9 that I've already finished will not be in the test. 5.1 will not be in the test. The test is specifically 4.1 to 4.8. I'm just getting ahead because, like I said, I kind of lost a day last week. I would have wanted to give you the test on last Friday if we didn't have a flex day on Thursday, but it was there. Not that I'm complaining, but it means I want to push back the test day. So I'm going on. In fact, I'll even mark off here. I have 5.1. So we're getting near the end, folks. Hang in there a little bit longer. We're almost at the end. I think we're done in what, less than a month, I would say. I think we're less than a month from finishing. Okay. All right, so I'm going to show you problem number 17. And this is one of those where I can't really show you the book and the work at the same time. So here's the problem. The velocity graph of a braking car is shown, used to estimate the distance traveled by the car while the brakes are applied. Okay, so see, they give you a picture in red of time versus velocity. Okay, so when we do these rectangles, base times height and so on, okay, the units are seconds times feet per second. And yeah, I think I'll write it in my book. Okay, seconds times feet per second. If you multiply seconds by feet per second, so when we go base times height, right? the time is in seconds. The height is going to be feet per second. When you multiply the units, the seconds cancel out, so you have feet. So that would be an estimate of the distance traveled. Okay. And by the way, this is actually done in some instances. If you want to estimate how far a car has traveled, a car steps on its brakes, or an object in space, right? Or you're sending some object into space, the space shuttle or International Space Station or anything like that. You estimate the distance traveled. Quite often, that's what they do. You have a time. Obviously, you can measure the time, and then the speed, right? So feet per second times seconds. And when I draw my rectangles, base times height, and so on, okay, base times height would be seconds times feet per second. So you're estimating the distance traveled in terms of feet. All right, so we're going from 0 to 6. I'm going to chop it up into 6 pieces. Okay. 0 to 6. Okay. Now it just says estimate. So we saw from yesterday, and maybe the day before, the best estimate would be if I pick the midpoints, right? So quite often, if I pick the left endpoint or the right endpoint, you get an overestimate or an underestimate. The best estimate period, quite often, is the midpoint. So when I go base times height, 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 and so on, okay, I'm picking the midpoints. Okay. So if you can imagine in this picture, I'll draw rectangles. So from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. Okay. I'm going to take the midpoint. So let me see if I can just barely get this. Go here, go straight up, and then draw a rectangle. Although I'm not really going to draw it, I'm just going to eyeball the midpoint. Same thing here. Go straight up, draw a rectangle, straight up, draw a rectangle at every midpoint, all the way through. So M6, M standing for midpoint. 6 means I'm chopping the interval into 6 pieces. All the bases are 1, so I'm multiplying by 1, which I like. If you multiply by 1, you don't do anything, right? Just leave it alone. And then the function value at the midpoints, f of 0.5, 1.5, 2.5, 3.5, 4.5, and 5.5. Okay, all the midpoints. Okay, so where are these numbers coming from? These are the midpoints. Okay, again, not sure I can show you at the same time, but okay, this is going to be a little bit of a chore. Okay, but take the midpoint, 0.5. If I go straight up, I got roughly 53. Okay, 1.5, I got 40. 2.5, I'm taking the midpoints, go straight up. Looks like it's about 30, halfway. 3.5, go straight up. It's a little bit below 20. I said 19. Right here, go straight up, 10. And halfway up there, seems like it's about 5. Okay, so the book's too heavy. Let me get that down. 53, 40, 30, 19, 10, and 5. Those are the function values at all the midpoints. Okay, so one more time. Taking all the midpoints. So if you were to draw it, you can draw it if you want to. I don't really want to do it here. And if we were meeting face to face, I'd have a way to show it to you using the whiteboard and stuff like that, but we're not there, so I can't do that. But the function value at that midpoint is about 53. This midpoint was about 40. This one was about 30. This one was 19. This one's about 10. This one's about 5. There it is. Add it all up, 157 feet. So that's my estimate of the distance traveled when the car brakes for 6 seconds. So that's what's happening here. The velocity of a braking car is shown. Estimate the distance traveled. We would say it traveled about 157 feet. Okay, so that's how that one goes. Okay, now let me go back and look at some other problems. We can go back to problem number 5. Estimate the area under the graph of f of x equals 1 plus x squared from x equals -1 to 2 using 3 rectangles and right endpoints. Improve your estimate by using 6 rectangles. Sketch the curve in the approximating rectangles. Okay, so I'm not going to do the 6 rectangles, I'll just do the 3. And then repeat using left endpoints, repeat using midpoints from your sketches, which appears to be the best estimate. Okay. So here we go. F of x equals 1 plus x squared. Parabola opening up. Okay. We know what x squared looks like. Just move it up 1. So there we go. Here's my little mini graph. It said go from -1 to 2. So from -1 to 2, plug in -1, you get 2. Plug in 0, you get 1. Plug in 1, you get 2. Plug in 2, you get 5. So there's the graph. I'm trying to estimate the area under this curve. From -1 to 2, n equals 3. Okay, what I have pictured are the left endpoints, using the left endpoints. Okay, I'll let you do the right endpoints on your own. Okay, so from -1 to 0, the left endpoint is -1. So go straight up, draw a rectangle. And that rectangle is clearly too big. Between 0 and 1, left endpoint is 0. Notice that one is too small, right? Because I lost that there. And then from 1 to 2, left endpoint is 1. Go straight up, draw a rectangle. So the rectangles are that one, and that one. Okay, so this one's too big. This rectangle is too big. I'm only supposed to have the area under here. I got all this extra space, but I lost this space and I lost this space. Right, so I add up the areas of all those. Okay, so base times height, base times height, base times height. All the bases are 1. I like multiplying by 1. And then all the heights. So what's the height here, which really means the function value, 2. Function value here is 1. Function value here is 2. Okay, in other words, the area of this rectangle is 2. The area of this rectangle is 1. The area of this rectangle is 2. I'll add them up. That's my approximation for the area under the curve. So 1 times 2 plus 1 plus 2, 5. Is it a good approximation? Kind of doubt it, but that's the best we can do for now. Now, if you could program this on a computer, chop this up into 1,000,000 pieces, the approximation would be very, very good. Okay, so as n gets bigger and bigger and bigger, or the language is n approaches infinity, then the approximation approaches a particular number. All right, so that was for the left endpoints. I'll let you do the right endpoints on your own, but I want to show you the midpoints. What if I pick the midpoints? Okay, so same graph. So all I did was I copied the graph, but my rectangle is going to be different. So -1, 2, 0, 1, 1, 2, 2, 5. That's the same. But now I want the function values at the midpoints. Okay. I'm still chopping it up into 3 pieces. So between -1 and 0, the midpoint is -0.5. Between 0 and 1, the midpoint is +0.5. And between 1 and 2, the midpoint is 1.5 or 3/2. Okay. Go straight up till you touch the graph, draw a rectangle. Go straight up till you touch the graph, draw a rectangle. Go straight up till you touch the graph, draw a rectangle. Okay, you can tell from this picture that the midpoint rule is going to be pretty good. All right, because in each picture, I gain something, I lose something. I lost this piece there, but I gained this piece there. Okay, gained that, lost that, gained that, lost that. Is it an exact calculation? Cancellation, I should say. Doubt it, but hey, it's worth something. So M3, M stands for midpoint. 3 is N, number of pieces that I'm chopping up into. L3, use the left endpoints. R3, which I'm not doing, but I'll let you figure out. So if I set this one up, you can do R3 hopefully, means you're doing right endpoints. So you say, how do I do right endpoints? Just do the same thing as I did for L3, except instead of picking the left endpoint, you pick the right endpoint. So instead of picking -1, 0, and 1, you pick 0, 1, and 2. Okay, so what are the heights? Not as convenient, but it's the function value at -1/2 plus the function value at 1/2 plus the function value at 3/2. Okay, so I plug in -1/2. Okay, -1/2 squared is 1/4. So 1 plus 1/4, 1.25. Then function value at 1/2. 1/2 squared is also 1/4. Add 1, 1 1/4. And in 3/2, 3/2 squared is 9/4. 9/4 is 2.25. Add 1, 3.25. Okay, add them all up, 5.75. Then part of the question was, which is the best approximation? The midpoint rule is probably the best, right? Okay, so you can see for the in midpoint, you gain some and lose some quite a bit, right? Like you normally gain one side, but you lose the other side. For the left endpoints and right endpoints, quite often it's going to either be an overestimate or underestimate. Okay. The one bad thing about the midpoint rule is when I get my answer, I'm not sure if I have an over or an underestimate. You can't tell. From using the left sum and the right sum, you can usually say, okay, I know for sure this is too big, or I know for sure this is going to be too small. Okay, so left and right endpoints sum, you can usually tell, okay, I've trapped the true area between these two numbers, right? This one's too big, this one's too small. If you just want a good estimate, but you're not sure if it's too big or too small, then that's what the midpoint rule is for. Okay. Okay, then number 7, kind of the same thing. Evaluate upper and lower sums for f of x equals 2 plus sine x. X goes from 0 to 5 with n equals 2, 4, and 8. So they want you to do the problem 3 times, chop it up into 2 pieces, 4 pieces, and 8 pieces. Okay, I'm only going to do the one with n equals 4. You can do the others. So if I do the middle one, right, you do the same thing, except 2 pieces, so it's easier, or 8 pieces, that's a little bit harder. Illustrate with diagrams. Okay, so I'll show you how to do that. Okay, 2 plus sine x, we take the basic sine function and move it up 2 units. Now the sine function does go through the origin. So the basic sine function goes like this, right? And shove it all up 2 units. So 0, 0 moves to 0, 2. This becomes my midline, goes up to 3, back to 2, goes down to 1, and back up to pi. Okay, so for upper sums, if I drew the picture like so. Okay, now, this is a little bit tricky. It asks for upper sums. So if it's your upper sum, you don't take the left endpoint, you don't take the right endpoint, you just take whichever is the bigger, and it's going to change in this particular problem. Okay. So if I go from 0 to pi over 4, upper sum would be take the value of 3. Okay. So let's chop it up into 4 pieces. So delta x is pi over 4. That's pi over 4, that's pi over 4, that's pi over 4, that's pi over 4. Okay. So I want the upper sum. Smallest is 2, the highest is 3. So I'm going to pick 3. between pi over 4 and pi over 2, the upper is still going to be 3. Okay. Then between pi over 2 and 3 pi over 4, the upper is going to be 2. And then between 3 pi over 4 and pi, the upper is still going to be 2. Okay, so you don't care about the left or right endpoint, just the largest number, the maximum value on an interval. So that's going to be 3 plus 3 plus 2 plus 2 is 10. 10 pi over 4 or 5 pi over 2. It's my upper sum. So this one's a little bit different. It doesn't ask for left endpoint or right endpoint. It just asks for upper and lower. So I'm picking whichever is the largest or the smallest interval. Now the lower sum, first subinterval, minimum is 2, maximum is 3. So what would the lower sum be? I picked a smaller number, which is 2. That happened to be using the left endpoint. Okay, between pi over 4 and pi over 2, again, the smaller number is 2. Okay, the next subinterval between pi over 2 and 3 pi over 4, this is 2, this is 1. So what's the minimum value? 1, which happens to be on the right endpoint. Doesn't matter if it's the right or left, I just want the smallest value, 1. And finally, from 3 pi over 4 to pi, the smallest value is once again 1, plug in 1. So that's 2 plus 2 plus 1 plus 1, 6 pi over 4, 3 pi over 2 is my lower sum. Okay, so for upper and lower sums, upper and lower estimate, okay, where'd it go? Yeah, upper and lower estimate, upper and lower sums, you don't pick the left endpoint or right endpoint, you just pick some point. Okay. All right. Then let's see, I'm almost done. So we can get ready to start asking questions. I should be able to give you some time to ask questions for the test. Okay, 13 and 15 are very similar. So I will show you 15. Oil leaked from a tank at a rate of R of T liters per hour. The rate decreased as time passed and values the rate at 2-hour time intervals are shown in the table. So I'll show you how to do 15, and your problem 13 is very similar. Find lower and upper estimates for the total amount of oil that leaked out. Okay, what I decided to do, let's see. Let's see, I actually don't have 15. I think I got the numbers wrong. I see what I did. Or did I? Yeah, I actually did 13, but I labeled it as 15. Okay, sorry about that. Let me just change that real quickly. Sorry, I take it back. I'll do 13 and not 15. That's what I did. Yeah. So 13, the speed of a runner increased steadily during the first 3 seconds of a race. Well, at least we got to talk a little bit about 15. Her speed at half-second intervals is given in a table. Find lower and upper estimates for the distance that she traveled during these 3 seconds. So what I decided to do was take these points and plot them on a graph. And once I do that, it becomes just like any others. Okay. So the points are 0, 0. 0, 0 makes sense, right? When the race starts, you haven't run anywhere. And then as time goes by, she runs faster and faster and faster, right? Up to the first 3 seconds. So I plotted 0, 0, 0.5, 6.2, 1.0, 10.8, and so on. And it ends up looking something like this. Okay, so in other words, 0, 0, 0.5, 6.2, 1.0, 10.8, all the way to 3.0, 20.2. That's what I plotted here. Time versus velocity. Here's 0, 0, and there's all the other ones. Okay, up to the last one, which was 3, 20.2. That last 3 commas point, that. Okay. So when I draw these high-rise buildings, so to speak, base times height is feet per second times seconds. So if I had seconds times feet per second, seconds cancel out, so we have feet. So we're going to have an estimate for the distance that she traveled. Right, so give lower and upper estimates, it asks. So here we go. Okay, now I didn't fill in the picture for all of them, but let's just take this interval here. If I wanted a lower estimate, this is between 1.5 and 2. The lower estimate, underestimate, would be to take the left endpoint. Upper estimate will be to take the right endpoint. Okay. Take that picture, apply it here and here and here and so on. I didn't complete the picture, but that's the general idea. So in this particular case, if I wanted a lower estimate, let's see, lower estimate would be all the left endpoints. Upper estimate, pick all the right endpoints. Okay. There are 6 subintervals, 1, 2, 3, 4, 5, 6. Okay, so when I do base times height, base times height, base times height, and so on, my delta x or delta t is 0.5, draw 0.5. And then for lower estimate, the function value at all the left endpoints. Okay, so that means it's like this. I'm not sure if I can do this well, but I'll give it a try. So between 0 and 0.5, right? She starts from 0, goes up to 6.2. So the lower estimate would be to say, okay, that first subinterval, she always went 0. Okay. The next subinterval, let's see if I can do this, between 0.5 and 1, she started at 6.2, went up to 10.8. Lower estimate would be say, okay, she always went 6.2. Next subinterval from 1 to 1.5, she goes from 10.8 to 14.9. So the lower estimate would be say she always went 10.8. So you're always picking the left endpoint as the function value and do the same thing all the way through. Between 1.5 and 2, she started at 14.9 feet per second, went up to 18.1 feet per second. So as a lower estimate, I'll just say she went 14.9 feet per second the entire time. Between 2 and 2.5, started off at 18.1, sped up to 19.4. So underestimate would be pretend she went 18.1 the whole time. And finally, the last half second from 2.5 to 3, she started at 19.4, went up to 20.2. So an underestimate would be say she always went 19.4. So I pick all the left endpoints. Here they are. I forgot the 0. 0 plus 6.2 plus 10.8 plus 14.9 plus 18.1 plus 19.4. That comes out to be about 34.7 feet. And then upper estimate, you can tell from the picture, I get an upper estimate if I take the right endpoints and that function value. Okay, so let me run through that logic again. I'll be done in less than 5 minutes. So after that, I'm done. If you want to start asking questions, you may. So in the first subinterval, I'm pretty much saying the same thing, except each time taking the right endpoint. So between 0 and 0.5, she starts at 0, speeds up to 6.2. So I'm getting an upper estimate if I pretend she runs 6.2 that entire subinterval. Between 0.5 and 1, she starts at 6.2, speeds up to 10.8. So if I pretend she ran 10.8 the whole time, that's clearly going to be too big. But that's what I'm going to do because I know how to find areas of rectangles, so to speak. All the way down the line, between 1 and 1.5, she starts at 10.8, speeds up to 14.9. So I'm going to pretend she went 14.9 the whole time for that whole half second. Same logic. Between 1.5 and 2, she starts off at 14.9, speeds up to 18.1. She's not going to run as far as if I pretend she went 18.1 the entire time, which is what I'm doing here. Between 2 and 2.5, she starts the interval at 18.1 feet per second, speeds up to 19.4 feet per second. We're going to pretend she ran a constant 19.4 feet per second, which means she's going to run a little bit farther. And finally, the last subinterval, she starts at 19.4, speeds up to 20.2. We will pretend she went 20.2 the whole time. Again, that's going to be too big. So that's what's happening when I take all the right endpoints. So I want to do base times height, base times height. All the bases are still 0.5. Here are all the right endpoints. 6.2, 10.8, 14.9, 18.1, 19.4, 20.2. You will notice the in-between numbers are the same. 6.2, 10.8, 14.9, 18.1. Okay. The only ones different are this has an extra left endpoint, 0. This has an extra right endpoint. Again, that makes perfectly good sense because if you look at the table one more time, see the 6.2 all the way to 19.4? 6.2 is the right endpoint from 0 to 0.5, but it's the left endpoint from 0.5 to 1, right? All the way down the line. Same thing for, see the 19.4? Is it a right endpoint or a left endpoint? Or both, right? 19.4 is the right endpoint if I'm considering the interval from 2.0 to 2.5, but it's the left endpoint if I take the subinterval from 2.5 to 3. Okay. So all the in-between guys are both left and right endpoints, except this first one. This first one, since it's the first one, it's a left endpoint, but it's not going to be a right endpoint, right? And likewise, this last one is a right endpoint, but it's not a left endpoint. So that's why this 0 is a left endpoint, but it's not duplicated here. This right endpoint of 20.2 isn't duplicated because it's not the left endpoint of anything. But all these in-between guys, everything from 6.2 to 19.4, right? So all the in-between ones on the table, 6.2 to 19.4, they're all duplicated because they're both left and right endpoints. It depends on which subinterval you're taking. Okay. This one is only a left endpoint. This one is only a right endpoint, so that's why they don't get duplicated. All the in-between ones serve as both left and right endpoint. It depends on what subinterval you have. Okay. And then add them all up, 44.8. All right, so that's it. So our estimate for those first 3 seconds is that our underestimate is that she ran 34.7 feet based on this data, and the upper estimate 44.8 feet. And if you just want an estimate in general, maybe you can average the two, right? So you might say she ran 39 feet, and then using the science lab language, plus or minus something, right? Plus or minus 5 feet or whatever. Okay, so you might report back, we believe she ran 39 feet, which I'm just averaging the two, plus or minus 5 feet. Okay, so that's the way that works. All right, folks. So I think I've covered everything I was going to do for today. So I don't think I have anything else in 5.1. Okay, so I'm going to declare 5.1 as done. Okay, and the rest of today, and then tomorrow also, I'm going to dedicate the time to questions and answers in preparation for the test on Friday. Okay, I'm not sure, but Prasanna, if you're there, Prasanna, you can tell the class about your study plan or having a study session or practice questions and so forth. So if you want to do that, you may. Okay, so I'm going to stop. Let me check the chat and see if anybody wants to ask any questions. Okay, and yeah, anybody who joined late, go ahead and put that in. Okay, so see that. And yeah, anybody else that joined late, go ahead and put that down. And I'll get started with some of the problems. Okay, and again, I'll dedicate all of tomorrow for this. Okay, in the remaining time, we don't have that much time, but I'll see what we can do. Okay, so let me just mark down what we have. So I got a request, all right. All right, and Prasanna, all right, thank you, Prasanna. So class Prasanna has sent to all of you, I believe, a sample type of test. Now, Prasanna doesn't even know the questions that I have, so, you know, you can't say, oh, yeah, these are going to be the questions on the test. Prasanna himself doesn't know. This was just his idea of a practice test, and I'd say that's fine. Okay, so let me see what people have asked for today. And anything I don't get today, feel free to ask again tomorrow. 11:15. Okay, let's see what I want to do. 4.331. All right, and Prasanna, I'm not sure if you wanted to, but if you wanted to do a study session or review session, you can go ahead and text the class or email the class. Not saying you have to, but if you want to. So 4.331. Okay, so all of this stuff here. Okay, this is actually very difficult to do all at once. So give it the old college try. .331. F prime is greater than 0 if x is not equal to 2. That means it's always increasing. Double prime. Okay, so stuff is happening at 2, clearly. Okay, so one, two. We have an inflection point at 2, 5. If you have an inflection point, you have a point. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. 2, 5 is an inflection point. You have that for sure. F prime is greater than 0 if x is not equal to 2. That means the graph is always increasing. So increasing, except right here. So right here, the derivative is not defined. So it's either going to be a corner point or a vertical tangent, most likely. Okay, double prime greater than 0 if x is less than 2, concave up. Double prime less than 0 if x is greater than 2, concave down. Okay, concave up, concave down, always going up. So let's see again. Always increasing, except at 2. Concave up if x is less than 2. Concave down if x is greater than 2, inflection point. And we have limits. Limit as x approaches infinity of the function is 8. 1, 2, 3, 4, 5, 6, 7, 8. So when I go way out here, we approach y equals 8. And when x approaches negative infinity, we approach y equals 0. Okay, so asymptote here, asymptote here. Always increasing, so first concave up. So I'll go like so, and how about I'll go up as a vertical tangent, undefined, and then switches to concave down, like so. All right, and that's the way this roller coaster works. Okay, and for you roller coaster aficionados, I've been on. Okay, yes, I've been on roller coasters. If it's too wild, I can't take it. But I've been on roller coasters that go like this, haven't you? Goes like this, goes straight up, and then brings you back like so. Okay. All right, so that's 4.331. Let's see now how much time I have for anything else. Okay, let's see. Prasanna has a review session on Thursday. Okay, so thank you, Prasanna, get that. 4.27 and 11. Let me see if I have time to get some of those out of the way. So mean value theorem and stuff like that. (4.2) number 7. Okay, Rose theorem. Verify the function satisfied, blah, 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 blah. Okay, so let me try to write that down. So f of x, oops, f of x equals sine of x over 2. It's best to treat it as sine half x. And you're going from pi over 2 to 3 pi over 2. This is problem 7 and 4.2. 4.2 number 7. Okay, this is a sine function which is continuous everywhere. So it's continuous everywhere. That means it's continuous from pi over 2 to 3 pi over 2. And it's differentiable on open pi over 2, 3 pi over 2. That's required. And then the third part of Rose's theorem is the two endpoints have to have the same height. I'm going to show that to you. Okay, so number 1, continuous on a closed interval, differentiable on open interval. How do I know that? It's a sine function. Okay, I know the sine's continuous everywhere. That means it's continuous here. It's differentiable here. Okay, now the function value. So f of pi over 2. So half of pi over 2 is pi over 4. Sine of pi over 4 is radical 2 over 2 from trig. And then 3 pi over 2, f of 3 pi over 2. Half of 3 pi over 2 is 3 pi over 4. And that's also radical 2 over 2. So yes, indeed, the function value is the same at the two endpoints. So by Rose's theorem, so there is some c between pi over 2 and 3 pi over 2 such that f prime of c is equal to 0, and find where that is. Okay, so what's the derivative of sine half x? Derivative is cosine half x times 1/2 by the chain rule, and set it equal to 0, which means cosine half x equals 0. So the cosine of what angles is 0? Okay, well, the cosine of pi over 2, so 1/2 equals pi over 2, or 1/2 x equals 3 pi over 2, for instance. Okay, going back to my unit circle. The angle between my finger is pi over 2, 3 pi over 2, and so on. Let's see, multiply both sides by 2. I get x equals pi. I get x equals 3 pi. That's out of range. Okay, but pi works. Pi is between pi over 2 and 3 pi over 2, is it not? Okay, so the c value that they want is pi. Okay, so that works. Let me do my focusing thing here. There's all that. Okay, and do I have time for one more? I think number 11 was asked for. Okay, so let me try 11. So same thing, except mean value theorem. F of x is 2x squared minus 3x plus 1. And we're going from 0 to 2. All right, it's a polynomial. Polynomials are continuous and differentiable everywhere. So that means F is definitely continuous on the closed interval from 0 to 2 and differentiable on the open interval from 0 to 2. So that satisfies the hypotheses of the mean value theorem. Okay, so let's find the slope. F of 0, 0, 0, 1. F of 2 is a little bit harder. 2 times 2 times 2 is 8. Minus 3 times 2 is 6, plus 1, that comes out to be 3. So I'm going from 0, 1 to 2, 3. Slope is y2 minus y1, 3 minus 1 divided by 2 minus nothing. That's 2 divided by 2, or 1. Okay, so mean value theorem says somewhere in the interval, the slope is 1, not 0, but 1, the slope of the line joining two endpoints. Okay, so there is a C somewhere between 0 and 2, such that f prime of C is 1. Okay, so I take the derivative, set it equal to 1. F prime of x is, what's the derivative? 4x minus 3. This time I set it equal to 1. And that's easy. 4x equals 4, x equals 1. Okay, is 1 between 0 and 2? It sure is. Okay, so the value of C that they want is 1. And I see that's all the time we have for today. All right, so I'm going to stop there today, folks. Let me do my focusing thing quickly here. And sorry, maybe I didn't do the focus thing for the other stuff that I did today. So maybe I'll get that quickly out of the way. So let's see, this was 17, the first problem that I did. Raising this up quickly. And then the stuff I did today, just for focusing purposes. So while I'm showing you this, I'll just blab a few more seconds. So tomorrow, come in with any questions. Some of you put some questions in the chat. Sorry, just ask again tomorrow. That'll be fine. So I don't have to do any new material tomorrow. Just take the whole time for questions and answers, and then be ready for the test on Friday. And then I think we're going to be okay. So give you all of that. Okay, so we're out of time. All right, so have a good day, everybody, and we'll see you next time. Okay, all right, bye, everybody. Have a good day.